In this video, we're going to look at the inverse of a matrix. The inverse of a matrix. And we're going to do very simple examples. We're mainly going to focus on just a 2x2 for now. But so given a square matrix A, again, that'd be like an n by n matrix. The inverse of A denoted by A inverse is a matrix such that A times A inverse is equal to the identity, and A inverse A equals identity. And again, if you have either one of these, the other one's going to be true. In other words, if you show that this is true, this is going to be true. If you show that this is true, this is going to be true. There's theorems that come up later that prove that if any one of these is true, the other one is true. Now, for a 2x2 matrix, the inverse is easy to calculate. Given A is equal to A, B, C, D, the inverse of A is 1 over the determinant of A, like this. And then what you do, you exchange these two. So D replaces A and A replaces D. So we just switch those. And we change signs of these two. So if this was positive, it becomes negative. If this was positive, it becomes negative. Or if it was negative, it will become positive. And now recall, of course, the determinant of A is for a 2x2 is given by upper left times lower right minus upper right times lower left, like this. And so let's do a quick example. So if we do, let's say our matrix A is given by this. Find the inverse. And again, let's find the determinant. Upper left times lower right minus upper right times lower left. So again, we have -6 for our determinant. And again, now apply this rule up here. Do 1 over the determinant. 1 over minus 6. And again, we're going to exchange the upper left and the lower right. And then change the signs on these two. And then multiply through by this scalar. Remember, when you multiply by a scalar, you multiply all the elements. And let's see if we can, you know what, I'm going to keep the, these fractions, they are not going to reduce them, because that might be helpful when we multiply them out if we don't reduce them, because I think when we multiply things out, we would end up making common denominators anyway. So let me just leave those on like this. So just double check. So this was negative 4, 6. The two negatives canceled, 5, 6. The negatives here canceled, 2, 6, negative 1, 6. So let's check. Let's see if this truly is the inverse. We just have to check one of the directions. So if we take A times A inverse, so what we think is the inverse, if we end up getting the identity, then we know it'll work if we commute these. Because if this works, A inverse A will also work. You only have to check one of these. So again, let's multiply them out. Remember, we multiply them, we're supposed to end up with the identity. If we don't, then what we think is the inverse here is not. If we do end up with the identity, then it is. And if we multiply this here, so we're taking the first row times the first column. Then the first row times the second column. I don't know if it's clear that that's a 5 right there. Second row times first column. Second row times second column. And let's see. So this ends up being 6, 6, which is 1. So we have 5, 6 minus 5, 6 is 0. 8, 6 minus 8, 6 is 0. 10, 6 minus 4, 6, 6, 6, which is also 1. So this does check. We multiplied A times this, what we thought was A inverse, and found out it truly was. Because if you take A times any matrix and you get the identity, it means this matrix you multiplied by is the inverse. Now, one thing you probably noticed about our inverse equation here is that we have one of the determinant. Therefore, if the determinant 0, we're going to have something undefined here. In other words, 1 over 0 is undefined. So we can say something pretty easily based on that observation. And now this happens to apply not only to a 2x2, but any matrix at all, is that if the determinant is 0, the inverse does not exist. So let me put this as a theorem. Again, here we can see it for a 2x2, but it actually is true for any matrix. Suppose that A is a square. Of course, square means it's an n by n. Number of rows and columns are the same. The inverse of A exists if and only if the determinant of A is not 0. Now, again, for larger matrices, to find the inverse is more complicated. We'll do that in another video. But for right now, you can, for any matrix, you can tell right away whether or not it has an inverse. If the determinant's not 0, it has an inverse.